Okay, am I on? Yes. Good morning, everybody. Welcome back to Day 100. We are now on week 5 of the class, so we are officially past the halfway point. We have about 3 more weeks of material left, but the 3 weeks of material that we have left are definitely the most conceptually challenging and most complicated pieces of material for the class. And so at the same time, they're the most exciting because in this part of the class, we'll learn how to actually fit some models to data, how to make predictions, how to know if our predictions are good or not. And so a lot of what we'll learn today is what you'll use in a machine learning job, if you ever take a machine learning job, or if you do anything related to statistical modeling or estimation. These lectures are the foundation for all of this stuff that continues on into more advanced classes like CS 189, or I believe Stat 154 or 155. I'm off by 1 there, I think, but I think it's one of those. And so the material that we're going over today will hopefully give you a taste of what it's like to do some machine learning and some prediction. At the same time, it'll be relatively fast, and in the past we've debated whether to split up this lecture into 2 lectures. I'm keeping it as 1 lecture on the schedule, but what's more important to me than sticking to my schedule is making sure that you feel like you have enough time to digest and process the material at a pace that makes sense to you. Okay, so as it is right now, this is scheduled for 1 lecture, but if things are confusing, what you should do is you should stop me and ask me to explain things again or to re-explain it another way, and that way I'll get a sense of whether the material is challenging for you. Okay, so if it is challenging, then what I'll do is I'll try to take my time to go through the slides today, and what I'll do is if we find that it's particularly hard, we'll go real slow, all right, and then we'll just move the rest of the lecture to tomorrow and then push back I'll work out the schedule. Okay, so basically I'll work out the schedule to fit your pace, but what we'll try to do is get through the material, and I really want you to understand this because linear regression and feature engineering is the heart and soul of machine learning, okay? All right. So homework 4 is due tomorrow, and homework 5 will be due Friday. Leo, if you guys are in Leo's section, he was out sick. I think he's been in the hospital for the past 4 days or something, and I hope that he's back today. If he's not back today, I might be covering his discussion section, but he said he's hopefully feeling better enough to leave the hospital and come back to discussion today. I told him that if he's leaving the hospital this morning, he might not want to go to discussion and teach it, but he said he's fine. We'll see what actually happens. But in any case, if you could let to prepare for Leo, that would be great. Or send him a card or something. That would be nice too.
Is it due next Friday or this coming?
It's this coming Friday. Yep. Okay, as I mentioned before, today's lecture might get split into 2. If you want me to split it into 2 lectures, you have to let me know. Okay. So to remind you of what we covered in the last few lectures, we talked about statistical estimation, where we take a sample and draw conclusions about the population. So for instance, we found out that if you have an unbiased estimator and you look at the sample mean, which we know is unbiased from last Thursday's lecture, if you look at the sample mean and you know that the sample mean is unbiased, then what you can conclude about the population is that this population mean is probably relatively close to your sample mean. It shouldn't be too far off. And on average, if you take lots of samples, the sample means will be centered at the population mean. That's what it means for an estimator to be unbiased. Okay, so we're drawing conclusions about the population from a much smaller data set, a sample. We talked about picking the estimator that minimizes the empirical risk or the average loss. So this is the procedure by which we decide what estimator is the best estimator to use for this particular population. Okay, so today what I want to do is show you how you can connect estimation with prediction in modeling. Okay, so before we were just trying to deduce a single number, and today we're going to move from deducing a single number to making some predictions about future numbers. And we're going to talk about linear models, which I consider our first foray into what we call machine learning, or what's commonly called machine learning. Okay. Talk about modeling. Okay, so the nice thing about modeling is that the idea of minimizing loss that we talked about for the last 2 lectures applies to modeling as well. So if we have a data set of cars, let's suppose that we like to predict the fuel efficiency, which for a car in the US is measured in like miles per gallon. In other countries, it might be kilometers per liter. But the idea here is that if a car is more efficient, it should be able to run farther while using less gas. Okay, that's kind of like what we're looking for. Okay, so we have this data set, and we have a data set of car attributes. And in particular, we're interested in making predictions about this MPG column. Okay, so you can imagine you tell me about your car. You tell me it's like a Toyota Corolla, which is what I drive. And you tell me like, it's at different attributes, it's horsepower, so on and so forth. And I'll be able to estimate for you this MPG that's associated with this particular car. Okay, so that's kind of the goal for today. Okay. When we make predictions, we choose a model. Okay, so the idea behind the model is, roughly speaking, the mathematical version of what I just described to you. You give the model some attributes about a car or about something you're interested in predicting, and it'll output for you the prediction. Okay, so here's a simple model, which is what we call the constant model. I'm illustrating the constant model to you because I want to go over some notation. Okay, so this f sub theta x equals theta here, on the f here is a function that outputs the prediction. The x here is our input data to the model, and then the right side of the equation is like the recipe that we use to compute the prediction. Okay, so for this particular model, what we do is we predetermine theta, and then we make some predictions. So let's say I set theta to 15. If I set theta to 15, then this model here will always predict 15, no matter what the car looks like. Okay, so that's what it means to be a constant model. Once you set theta, it just outputs that value of theta forever. It won't do anything else with what you give it about cars. Okay. In contrast, a simple linear model will write like this. Okay, and so this particular model says, give it a number here, x, and then it'll output theta 1 times x plus theta 0. And this is just a fancy way of writing like the line, right? So a line is like ax plus b. In this particular case, I swapped out a and b with theta 1 and theta 0. The reason why I've done that is because we're talking about multivariable linear models. And with multivariable linear models, we'll have theta 2, theta 3, theta 4, so on and so forth. Okay. Of particular note here are these parameters that we call theta. You'll hear them being described as model parameters or model weights. Okay, so I will usually call them model weights, or I'll try to call them model weights, in order to not confuse you with the population parameter. Okay, so the population parameter is like this unknown quantity of interest in the population. You'll hear people say these guys are model parameters. I'll call them model weights. Okay, so that way we won't get too, hopefully we can try to avoid some ambiguity about what's a parameter and what's a weight and what are we estimating. Okay, so these model weights, we're trying to pick the model weights that make the model have the best fit to the data. That's essentially what it means to do modeling. Okay, so we can start simple by looking at the constant model. Okay, so we have this unknown variable theta. And I mentioned before that in order to make the model, in order to fit the model to some data, we want to choose the best value of theta. And the question is, how do we do that? Okay, so if you remember your linear regression from data 8, you might remember how to compute like the slope and intercept of a regression line. We'll go over that briefly today, and then we'll extend the idea to do multivariable linear regression. But the same idea applies to basically every model. Okay, so almost every model will have some parameters theta. Maybe it'll have more parameters like theta 0, theta sub 1. Maybe it'll have like a ton of parameters like a neural network. But the idea behind all of them is the same, which is pick the parameters that makes the model most closely resemble the data that is trained on. Okay, so let's talk about the constant model. We have this model, and the idea here is that if the model can only predict one number, then we should pick the number that's closest to most of the values in the data. Right, so I have here some miles per gallon for cars, and for the constant model, you might imagine that I will pick the theta value that's close to most of the values in this data set. Okay, so if I have MPGs and like all the MPGs are like very close to like 16, then it'll probably be a good idea to set this theta in the constant model equal to like 16. Okay, any questions about this? Okay. So what I'll do is I'll write down some more notation. Okay, so I'll say that x sub I is what we use to make predictions, and y sub I is what we're trying to predict. The reason why I'm doing this is because in a single sample, you have both x and y, right? So you saw that big old table I had on the previous slide with the car attributes and the miles per gallon. Usually what happens is if you have a single sample, you have one column you're trying to predict, and you use the rest of the columns to make a prediction. Okay, so what we'll say is that the y sub I are the values you're trying to predict, and the x sub i's are the values you're using to make a prediction. But they both come from a single sample. Okay, so the reason why I'm like splitting apart the sample into x sub I and y sub I is because in a single sample, there's both what we use to make the prediction as well as what we're trying to predict itself. Okay, so we'll turn our intuition into a mathematical idea. And the mathematical idea is we'll pick the value theta that minimizes the average loss between the y's in our sample and the predictions of our model. Okay, and if you remember, the average loss looks like this. And what I've done here is I've replaced, so last week we only saw theta in this in this part of the equation. I replaced it now with f sub theta. The reason why I replaced it with f sub theta is because this f sub theta is our model's predictions. So this is the notation I'm using. Whenever you see this guy right here in the equation, you should think to yourself, these are my model's predictions. Okay? This loss formula is computing for every prediction of my model, find the difference between my prediction and the real value, square the errors, and then take the average. Yeah, Danny?
Should that x be an x sub I?
Yes, my bad. It should be an x sub I. For the constant model, it doesn't matter at all because the constant model doesn't use the x sub I, like doesn't use this input at all. But yeah, for future models, you'll see me like replace this with x sub I or capital X sub I, depending on what we're working with. Good point. Okay. I also realized that I always forget to put like the summation, what we're summing over on the summation, which is not super good of me. But whenever you see the summation, you can assume that it's from like I to n. Okay, so I is like the subscript here, and n is the number of points in our sample. I apologize for that. But do remember that I'm summing over all the points in my sample, taking the loss for every point. Okay, so I have this loss formula. And now we can plug in our constant model. Okay, so since we have f sub theta equals to theta for a constant model, I replace f sub theta with my model. But you'll notice here that this looks exactly the same as the expression for loss that we had from last lecture. So it's the exact same expression when we were trying to estimate the mean of a population, right? And so since this is the exact same expression from last lecture, and we worked through the calculus last lecture to take the derivative and set it equal to 0, we happen to know here that theta equal to sample mean is the best model parameter. Which essentially means if you want our model to predict values that are close to most points in our data set, one good choice is the sample mean. Okay, so I'm trying to refresh to you here like some ideas from loss. I'm also showing to you here, you can reframe the loss framework in terms of predictions, but the same idea of loss minimization applies, right? So I'm still minimizing loss. The only conceptual difference here is that I'm trying to minimize loss to make a prediction about future values instead of trying to estimate something inherent about my population. Okay, but really those two things are the same, right? So modeling and estimation are like, you can think of them as two sides of the same coin, right? So estimation is like making our best guess at the parameter in the population, while modeling is trying to make predictions. So if I get a new value from the population, what's my best guess as to what that value is? And the reason why there are two sides of the same coin is because oftentimes in modeling, what we're doing is we're making some assumption about how the population generates values. For example, what I'll write here is what we call like the population model, so to speak. And I'll denote things related to the population, as always, with a star. Okay, so this star here says, I assume that my population generates values by taking a single parameter and adding some noise to it, epsilon. So this particular assumption about my population says that for car MPGs, for example, I'm going to assume that all the MPGs are centered around, let's say, like 17, the population parameter. But when I collect data, I'm not always going to get 17 because I'm going to have some noise. Maybe I'm going to record the MPGs incorrectly. Or maybe it's just the case that like when you manufacture cars, it's going to aim at 17, but it's going to be off sometimes based on like how the car was actually put together. Okay, so this epsilon here says the population, when you collect data, there's noise somewhere in that data collection process. Okay. And so, but you should read this as an assumption about the population, not like what the population is doing itself, right? So what I'm doing here is I'm saying, okay, I'm going to assume or pretend for now that the population generates all of its values by just taking the average, like some parameter and adding some noise to it. Okay. And so in estimation, we're trying to estimate theta hat, which we want to be close to theta star. And so we talked about Wednesday and Thursday. Okay, so the estimation procedure is trying to find the closest value to theta star, but modeling is essentially saying, well, take that theta hat and use it to make some predictions. Okay, so what we'll do is instead of just finding theta hat, modeling says, I'll make a model and I'll put theta hat in my model so I can make some predictions about what I think future population values should be. So behind every model that I'm going to explain in class, there is like some underlying assumption about the population. If that assumption is violated, then your model will perform poorly. And that's kind of just the way things go. Okay, so let's go over pictorially how we go through this modeling process. Okay, so I'm going to draw for you a diagram, and on this diagram, the things that we, the data scientists, have control over, I'm going to put in blue boxes. Okay, so we start off with some input data. We pass that input data into a model. That model has model weights that we set beforehand in order to make predictions. Okay. For this particular model, it's a constant model, so all the predictions will be the same. So we have 15 here for all of its predictions. And then we'll give those predictions into a loss function, and the loss function computes the loss on every point, and the overall model loss is the average of all of these losses. Okay. And so the idea here is that if we tweak theta, we're going to impact the predictions, which is going to impact the loss. And the idea behind fitting a model is we want to fiddle around with theta until we get the theta that minimizes the average loss here on the right-hand side. Okay, any questions about this diagram? Okay, now I highlight to you the things in blue because it turns out there's only like 3 things in this diagram that you really have control over. You don't really have control over like what these numbers are here, but you do have control over what you choose to be your model, what you choose to be your loss function, and how you fit the model to that loss function. And so it turns out that pretty much all of modeling can be reframed in terms of like tweaking one of those 3 boxes. And I'll show you what I mean. I was supposed to show up one at a time. Okay, but here we go. I'll show you this big table. And this big table essentially says, if I choose a model and I choose a different loss function, I get all these machine learning techniques. Okay, so basically like if you take a machine learning class, they're going to talk to you about like tons of models and tons of loss functions. But if you remember that the basic procedure here is you pick a model, you pick a loss function, and you fit the model to minimize a loss function, then you can essentially can recognize that all of these techniques here are just variants of the same modeling recipe. Okay. So the reason why we're going to spend like a bunch of time on linear regression and not much else in this class in terms of modeling is because linear regression turns out to be like a very powerful modeling technique that also extends itself naturally to many other types of modeling techniques. Okay, so the idea behind by explaining to you linear regression, I will have to go over like what this model is, how to pick a loss function, and all of that jazz that also applies naturally to pretty much every other machine learning technique out there. A neural network is essentially a complicated model here, a complicated loss function here, but it's the same idea of like picking the parameters to minimize your loss. Okay. You may also notice that most of these models here in this table look very similar to each other. Okay, so this is like theta.x. I haven't explained to you this notation yet, but we'll get there when we get to multivariable linear regression. But you can read this as essentially a linear model. So all of these models here are linear models. This one right here is like a variant of a linear model called a logistic model. And we'll go over this guy in particular in detail when we talk about logistic regression. But really, like linear modeling gives you like tons of choices in terms of like what kinds of patterns you can fit in data. And I hope to show you that linear regression can do a bunch of stuff for you in this lecture. All right. Let's talk about linear models. Okay, so we've talked so far about constant models. But we know that if we're actually trying to predict some attributes of a car, or if we're actually trying to predict the MPG of a car, we can do a lot better than a constant model by incorporating some more information. Okay, so for example, if you look at the horsepower column, we can notice that if you plot horsepower and MPG, in general, if a car has more horsepower, it has less miles per gallon, it's less fuel efficient. So if you want a race car, you have to give it gas like all the time. Okay. And so the idea here is that if we can find some variables that are correlated with our variable of interest, the MPG, then we can hopefully make better predictions by capturing more patterns in the data. And that's more or less what the linear model is trying to do. The main advantage of a linear model over a constant model is that it makes use of other features or other data in your data set. Okay, so we want our predictions to depend on the input data x, and as I showed you before, we have the linear model here. The F star here is kind of like our assumption about the population. Okay, so for simple linear models, oftentimes the most common assumption is that the population values are generated according to a linear function plus some noise, and usually we assume that noise is normally distributed with mean 0 and some some variance sigma squared. Okay, so you should read this as values in my population are generated on a line with some noise. Okay, and we try to fit these values from our population by fitting a line to our data. Okay. Here's where things start to get tricky. So as usual, we can minimize the loss. So if I pick this model, and I pick, let's say, the mean squared error loss, then the only thing left to do is to minimize that loss. And we can minimize the loss by taking the derivatives with respect to theta, but we have two parameters in this particular model. We have theta 0 and theta sub 1. Okay, so the idea here is that if I fiddle around with theta 0 or theta 1, I'm going to affect my loss. And what I want to do to minimize the overall loss is to pick both theta 0 and theta 1 so that the loss is as small as it can be. Okay, so we have two parameters. And what I've done here is that I've written the loss equation that involves two parameters. I've taken my model here and replaced it with my simple linear model. So what I've done here is this is the loss, the average loss for the simple linear model using the mean squared error loss function. Okay, so I've plugged in my model into the loss function, and now we can take some derivatives in order to find the minimizing values of theta sub 0 and theta sub 1. All right, so you have this formula. I can take the partial derivative with respect to theta 1. This is the partial derivative. How did I get this? I apply the derivative rules. So I moved, for example, if I have something squared, the derivative rule is move the exponent as a multiple, subtract 1 from the exponent, and then apply the chain rule on theta sub 1, which is negative x sub I. So I have negative x sub I here. I can do the same thing for theta sub 0. Okay, so similar idea. I'm moving the exponent down to a constant, subtracting 1. And here, the constant in front of the chain rule applied to theta sub 0 is negative 1. So I have negative 1 here for the partial derivative of this equation with respect to theta sub 0. Okay. Now you can go through the algebra, right? So if I wanted to actually solve for theta sub 1 and theta sub 0, what I would do is set the right-hand sides of these equations equal to 0. And then I would solve them. Solving them actually is very complicated because each of these equations has two parameters, theta sub 0 and theta sub 1. And so if you want to solve these two at the same time, you have to solve that system of linear equations, which is a big pain. Okay, so I'm not going to do it on these slides because I don't want to intimidate you. And it turns out that it's not super important for complicated models to be able to solve these guys analytically. So I will not ask you to solve these analytically on a homework or an exam, but you should know how to set this up. Okay, so I'm going to skip to the answer. And the answer is familiar if you're taking data 8. The answer here is we let this variable r be the average of the products of x and y when both variables are measured in standard units. And then theta hat sub 1 is this formula here. Theta hat sub 0 is this formula over here. Okay, so this is from data 8. And it turns out that if you work through the math on the previous slide and set everything equal to 0, if you want to practice your algebra skills or practice your loss minimization skills, I suggest you can try it out at home. And what you should get is something that looks like this. Now, you're going to get R in terms of some math formula, so it'll be some crazy summation. But basically, you should ideally be able to derive it yourself, but that would be that'd be considered a very high difficulty problem on, let's say, an exam. A much easier variant that I could, in theory, give you on an exam is I give you a linear model that has no intercept. Okay, so I don't have this theta sub 0. And I ask you to solve for theta sub 1, that's something that's much easier to work with algebraically, and that's something that you should be able to do. Okay. The takeaway here is that sometimes the algebra gets hairy, but the same idea still applies, right? So no matter how hairy the algebra gets, the idea here is that we're just trying to minimize a loss. And the way we minimize the loss is by taking some derivatives. Pause for questions. Okay. Now things will start to get really hairy. Let's talk about multivariable linear models. In a multivariable linear model, instead of using a single variable to make a prediction, we're going to graduate from data 8 and use more than one variable. We're going to use up to p variables. Okay, so this model here says, do the same thing as a simple linear model, but take into account many attributes of my data instead of just one attribute. For example, if I'm trying to use horsepower to predict MPG, I can also use a number of cylinders in a car, and I can call that x2. I can use the year the model was built, the year the car was built, and call that x3. I can use the different parameters in my data set and call those x4 and x5 and x6. And I can essentially combine all those attributes together into a single model, and that's what we call a multivariable linear model. Okay, so I do have some notational things to go over with you. The first thing is that bold X is a vector that contains one row of input data. Okay, so if you see bold, in this class and in the textbook, I'm almost always going to mean a vector of data or a matrix of data. Lowercase letter bold means a vector. Capital bold letter is a matrix of data. In this case here, this is saying, take one row from my data set, feed it into, multiply all the values together, add them up, add an intercept term, and that's my model's prediction. Okay. so here's some intuition about this. Let's suppose that we're trying to use both the horsepower and the model year to make a prediction about the miles per gallon of a car. I expect that theta sub 1, if theta sub 1 is the horsepower model weight, and will be negative, and theta sub 2 will be positive. Why do I expect that? Because I can plot MPG versus horsepower and MPG versus model year, and I can see in my data that as horsepower goes up, the MPG will go down, and as the model year goes up, like as the car was more recently built, the MPG also goes up. So I expect that if X1 increases, F should decrease. I expect that if X2 increases, F should increase along with X2. Okay, so I'm encoding mathematically the intuition that I have like in English, all right? Okay. All right, so here I'm going to introduce some more notation. Here we go. So I have this formula here, and it's really long. Okay, so I don't want to write this every time I talk about a multivariable linear model. I'll do a trick, and the trick here is add a column of ones to the table. So I have here MPG, and I have here horsepower, weight of the car, and model year, and I'm going to include a column that I call the bias. The bias column will be all ones. Okay, so the first x vector will be 1, 130, 3504, and 70. It'll be 4 elements. The second x vector will also have 4 elements. The third x vector will also have 4 elements. Okay, so here's my x vector. It'll be 1, and then x1, x2, x3 for each column in my data. And I will have 4 parameters, theta sub 0 through theta sub 3. Okay. And if I write down these vectors like so, I can write our model very succinctly by just writing my prediction is theta dot product with x. Okay. So what I've done here is I've like manipulated my data a little bit so that when I write down my model, I can write it very simply by relying on like this inherent dot product operator in linear algebra instead of writing down this thing up here. But these two are equivalent. Yeah?
Where does the 1 come from in bias?
We just arbitrarily do it. So I just say like let's add a column of ones, and it turns out that adding a column of ones makes life easy. You can also view this if you've had some experience with like linear algebra. You can also view this as adding another like dimension to our matrix, our data matrix here, which lifts our data matrix into like a p+1 dimension, and then like in that dimension we have a dimension for the intercept term. But basically the idea here is, practically speaking, if you add a column of ones here, the dot product of x times theta is exactly the same as the one up here, because you'll do theta sub 0 times 1, which is theta sub 0, plus theta sub 1 times x sub 1, which is the second term, theta sub 2 times x sub 3, add those all together. Yeah?
So the reason we're doing this is just because there's one extra theta term that if we add this column of ones, it makes it easier to write.
Yeah, so it's notational addition, but you can imagine here that if I did not care about the intercept whatsoever, like if I just want my line or my plane to always start at the origin, then I can just drop this intercept term here, and I can still write theta times x or theta dot product x without the bias column. Okay. It turns out that once you can write some dot products down, it's relatively easy to get some matrix products in here, and so we can write a lot of modeling ideas in a very succinct way by relying on some tools from linear algebra, which are matrix multiplication and vector multiplication. Okay, so I'm going to go over that notation with you. So first, the bold lowercase y is a column vector of sample points to predict. Okay, so bold lowercase y here contains the values 18, 15, 18, blah, 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 32, 28, 31 in a vector, a column vector. I'm going to say my bold uppercase matrix X is the matrix that contains all my input data. And this input data is, I'm going to say, n rows by p columns. Okay, so usually when I write n here, n will refer to the number of data points, and p will refer to the number of dimensions in my data. Sometimes you'll see n by d in other books or other classes, and those are the same thing. So usually, like, people will use d or p here. I'm going to use p. Okay. Boldface x sub I is a row of input data. Lowercase x is input data, but doesn't refer to a specific row. Okay, so if I write x sub 1 here, this refers to the first row of my data. If I write capital X sub 2, this refers to the second row of input data. But oftentimes, I just want to work with a row more generally, and in those cases, I'll just use the lowercase x here. The bold here still means that it's a vector or a matrix, right? Okay, so I have here the matrix, I have here a vector, and I have here a vector. The reason why this is a vector here, the capital X sub I, is you can imagine that when I add a subscript to a vector or a matrix, I drop down to the mathematical object of lower dimension. So here, when I add a subscript, I go from a matrix to a vector. When I add a subscript to the x here, I go from a vector to a value. Okay, so if I write x sub 2, and I'm referring to this particular row here, then x sub 2 would be 165. And I would not bold it because that would be a scalar. It would be a single value. Okay. Boldface theta is the vector model weights. And boldface theta hat is the loss minimizing model weights. Okay, so it's a vector that contains the model weights fit after we fit the model to the data. That's why we put the hat on it. Okay. So now you've seen this notation, why don't you try working with it? So write a matrix expression that computes a vector with a fitted linear model predictions for all the sample points at the same time. You can't write a loop in math, but you can use matrices, so try it out. And again, I see some of you guys bringing out paper. It's a great idea because you will have to work with matrix algebra on paper very soon in discussion and in your homework probably. Okay. Once you're done or have made some progress, why don't you talk it over with your neighbor to see whether, if you're both stuck, whether you can help each other move forward, or if you have an answer, if you can compare with your neighbor your answer. Go ahead. Okay, let's try it out. Okay, so the first thing you should do whenever you write anything involving matrices is to write down the dimensions of what you want. Okay, so if I want the predictions for all sample points, what are the dimensions of this particular vector here? It's a vector that's n by 1, right? N rows and 1 column. Okay, so that's what I'm aiming for. I want an n by 1 output. Okay, now if I'm confused, what I can do is try to work with what I know how to do. Okay, so how do I compute the prediction for 1 point? The prediction for 1 point is theta hat dot product with x. Right, so if I don't know how to write the expression for all the points, I can make the problem simpler by just finding the prediction for 1 point. And maybe that will give me some progress on how to move forward. Okay, so I have here theta hat dot product x is the prediction for 1 point. There it is. Okay, now if I want the prediction for all the points, what I can do is just stack up all the theta dot products into one long vector here. Okay, so here I have theta hat dot product with the first row of x, theta hat dot product with the second row of x, theta hat dot product with the nth row of x. And I know that this is right, or gets me closer to the right answer, because the dot product is a scalar, it's a number, and I have here n rows in this vector here. So this vector has the right dimensions, even though it involves some complicated matrix-looking things, because I know that the number of rows is n, and the number of columns is 1. Okay, now to write this more succinctly, I can deduce that this vector here is equal to the matrix x times theta hat. So this right here is what I was looking for in terms of the answer. It's simple, but the actual procedure to get to this is not that easy, right? The way you work with most of these, until you get very familiar with like matrix multiplication and all of that jazz, the way you actually figure these out is to start with something very simple and then build it up and then try to figure out how to like simplify this into a matrix expression. Yeah, Matt?
If we have the matrix X with dimensions n by p, does that mean that our theta hat vector is p by 1?
Yes. So that's a great question. So the question was, if x is n by p, is theta hat p by 1? It turns out it is. The reason why, okay, so you might ask me, wait, you wrote down theta hat dot product x. Why is it x times theta here instead of theta times x? The reason why is because I need to match dimensions. Okay, so if I write theta times x, I will get something that's like it has the right idea, but the dimensions don't match up properly. So if I reverse these two terms here, I do p by 1 times n by p, which doesn't work out. On the other hand, if I write down n by p times 1, the middle dimension works out, and the final result is n by 1, which I know is what I want. And so I'll give you like a pro tip, which is that oftentimes if you're totally stuck, if you write down something that computes the right number of dimensions, chances are you get very close to the right answer. Like if you look at the stuff I had in the previous slide, there's only a few combinations of things that give you an n by 1 vector, and this is one of the combinations. Yeah, Ruby?
Does p include the intercept? I was like, I'm confused why it wouldn't be p plus 1.
Yeah, so the question is, does p include the intercept? The answer is yes. I'm using p a little sloppily here, but in this case, I'm assuming that the intercept term is already like added to x. Yeah. I just don't want to have to write like p plus 1 everywhere. So usually when I write down p, you can assume here that I'm including the intercept term in x. But it still applies whether or not I include the intercept, right? So if I include the intercept in x, or I don't include the intercept in x, this multiplication here doesn't really care about that, as long as the x and theta have the right dimensions. Okay, want to try one more? Let's try one more. Let's write the expression that computes the average mean squared error loss for all data points. So again, if you check the dimensions of this, the average mean squared error loss is a scalar. It's a single number. So you should get out a single number as your answer. See if you can write a matrix expression that computes the loss. Go ahead. Okay, talk it over with your neighbor and see if you can help each other make some progress on this one. Okay, so again, the first thing you should do is start off with the dimension of what your output should be, which we happen to know in this case is a scalar. The next thing to do is, if you get stuck, break up the problem into something smaller that you can still solve. Okay, so instead of solving the average loss for all data points, you might want to find the loss for a single point. The way you find the loss for a single point is you write the expression on the right of the summation here. Okay, so here I have the prediction for one point. Here I have the real value for that point. I've subtracted the two and taken the square. And this is the loss for a single data point. I can take the average of those losses, and now I have the average mean squared error loss for all data points. Okay. And this right here, actually, if you wrote this, I'll be pretty satisfied. If you want to be fancy, you could eliminate the summation here and write this. If you eliminate the summation, then you might remember that if you take the magnitude of a vector squared, you'll get essentially the summation of the squared elements of the vector itself. Okay, so right here, I've gotten rid of the summation by saying instead of summing over every value in y sub I, just take my whole vector y and subtract it with all my predictions at once in one go. Okay, and again, this notation here, it says the magnitude of v is equal to v dot product with v, which is also equal to v transpose times v. So all of these expressions here are the same. On a lot of other books or machine learning classes, you'll see v transpose v instead of v dot product v. I happen to use v dot product v because this is a little bit less like finicky about whether you have a row vector or a column vector. Okay, so you may ask me, why go through all this work? One reason to go through all this work is to show you that once you write things in matrix form, oftentimes the expression looks very similar to when you weren't using matrices to begin with. So if I told you that my model was a times x, right, like a line with no intercept, then you might expect the loss to look something like 1 over n times the sum of yi minus a times x. And you'll notice here that this expression is very similar to what you would write if you weren't using matrices to begin with. Okay, so I'm trying to show you here that the reason why we use matrices and vectors and all of this stuff is to generalize what you already know about numbers. Okay, matrices put numbers into like a single list or an array or matrix, and because of that, a lot of the expressions that we come up with that involve matrices are very closely resemble the expressions that we have that involve scalars. Okay. The second thing is that writing this in Python is like 100 times faster than writing a for loop. Okay, so the second reason is if you were actually put these numbers into a NumPy array or NumPy matrix and do this calculation here, instead of writing the for loop over here, your code will run way, way faster because NumPy is very good at multiplying matrices and vectors together, while for loop is not that good. The third reason, which I'm going to go over in much more detail tomorrow, is because once you have these terms in matrix form, taking the gradient or taking the derivative of this is much easier than taking the derivative of n linear equations. Okay, so if you want to try to solve for theta, if you want to minimize loss by solving for theta here, it's a lot of work to go through like a ton of linear equations and solving them all at once. Instead, the much easier thing to do is to put it in matrix form and use matrix algebra to do some computation. Okay, so 3 reasons. 1, to show you how linear algebra is useful. 2, because it's more efficient. 3, because it's useful when we actually do some manipulation with these expressions. Okay, which means that you should really practice interpreting these equations and practice working with them. Okay, so you should be able to make sense. If I write down anything on the slide in the future, you should be able to immediately know, okay, I know the dimensions, it's a loss. Or I know the dimensions, it's the predictions. Okay. So I have here an expression for the model. Okay, so let's backtrack a little bit. The whole point of this exercise was because we wanted to write down the multivariable linear model, and then now we can try to fit that model on some data. right? So I have here in the loss, this term right here is my model, and this whole expression here is my loss. And now what I want to do is I want to tweak theta to minimize the loss, as usual. Okay, so nothing changes just because I'm working with matrices. Once I write it down in matrix form, I still have parameters to change, and I still have loss to minimize. Okay, so the question is, how do we pick theta to minimize loss? Well, what I can do is take the partial derivatives for theta sub 0, theta sub 1, all the way up to theta sub p. Okay, so this would essentially be the equivalent of what I did for the simple linear model. Right? For the simple linear model, I did the partial derivative for theta 1 and then the partial derivative for theta 0, and I just skipped to the solution there, and I show you that if you solve those equations, you get like the correlation coefficient, you get some like weird stuff going on. Okay. And we can do the same thing for the multivariable linear model, but it gets really, really hairy. So what we'll do instead is take the gradient and set it equal to 0, which solves for all the model weights at once. And if you remember, the gradient of a function L is the partial derivative of L for every element of the vector you're taking the gradient for. Okay, so the gradient of L with respect to the vector theta has one element for every element in theta. In other words, if theta is p by 1, so p rows and 1 column, the gradient of L will be p rows and 1 column. There are p rows in this vector. Okay. I won't go through like all this math today. We'll save it for the gradient descent lecture tomorrow, or perhaps the day after. But you should essentially know that the gradient is like the matrix, like the mature, or the sophisticated, or the grown-up way to work with the derivatives when you have a bunch of parameters. Okay. So I'm not going to go through the derivation, but I'm going to show you how that derivation, what the result of that derivation is. So if you take the gradient of the loss, set it equal to 0, and solve for theta hat, you get an expression that looks like this. It's complicated. You have like matrix transpose times a matrix, the inverse of this times a matrix transpose times a vector. But again, you should remember that the output of this needs to be p by 1, because that's what theta is. And so what you should do is practice going, like you should take this expression here, and you should be able to write down the shapes for every matrix term, and prove to yourself that the output of this expression is p by 1. Okay. Now, this equation here has a special name. We call it the normal equations, or normal equation. The reason why it's called normal has to do with like the fact that these vectors are like some vectors in these expressions are orthogonal to each other or normal to each other, but really you can just remember them as the normal equations. Okay, and these give a closed form recipe for fitting a linear model, which means that if I have matrices x and y, I can solve for theta immediately. Okay, so I don't need to go through like all the work of doing the derivation again. Just like how for the constant model, I can fit the constant model by just saying theta hat is the mean of my sample points. I fit a multivariable linear model by saying that theta hat is equal to this. It's a long expression, but it's a recipe. I can put this recipe into Python and fit a linear model the same way I could fit a constant model. Okay, so again, you should go home, figure out the matrix shapes in these equations. Okay, now, one of my slides. I think I hit it by accident. I'm going to unhide it. Unhide this. Don't skip it. Okay. Now, it turns out that in practice, we will very rarely use normal equations. The reason why I show it to you is because they're very common, and they also contain some mathematical insight, which I believe we talk about in the book in like the geometric perspective of linear regression. But in practice, this right here is mostly used as like a mathematical demonstration, more so than as an actual technique we'll use to solve. And the reason why we don't use it in real life is because inverting a matrix takes a long time. Okay, so if you have an n by n matrix, then that'll take at least O of n squared time. O here I'm using interchangeably with theta. Okay, so if you know like theta and 61A, the O here is essentially saying like the time it takes to invert the matrix is quadratic with the number of points in my data. Which means if I have 1,000,000 sample points, it'll take a long time. Okay, and it's not that uncommon to get like millions of sample points, or maybe even like tens of millions, or maybe even billions, depending on like how big your data set is. And so essentially, if you have data sets that are large, this is like a nightmare to you. You don't want to ever work with something that has quadratic time on your data, because you'll like never finish computing your algorithm. And in fact, the state of the art in terms of inversion is O of n to the power of 2.3, and there's like a competition right now in like algorithms to like find the fastest way to invert a matrix. But I believe it was proven maybe only like a decade ago, that the best you can ever possibly do is n squared. Okay, so it'll take a long time no matter what. So basically, you never want to do this. The reason why, and you don't want to do this because it takes too long. So instead, we'll talk about gradient descent next lecture, which doesn't use this analytic solution, but it approximates the solution in a much faster way. Okay. For small data sets, I would say anything under like 1,000,000 points, you can probably use this and do the answer that way. So I'm going to show you a demo. And I have some more content here on feature engineering, but I will save that for tomorrow. So I'm going to do my demo, take attendance, and we'll call it a day. Okay. So after all of that work, we can now fit a model to some data. So I have here the MPG data set. I have here 392 cars with a bunch of attributes here. Okay, and I want to predict again the MPG column. Okay. As before, I can show you what the data look like or how they're correlated with MPG. So as always, I can take the LM plot. I can plot horsepower on the x-axis, MPG on the y-axis, put in my data, don't fit a regression line. And here I see that horsepower and MPG are negatively correlated. Change this to model year. See that the model year are positively correlated, which you can interpret as saying modern cars have better miles per gallon. Okay. So I'm going to write down the columns that we're using to make a prediction, and I'm going to create my data matrix X. Why can I not type hello? Okay. MPG.assign bias equals 1 gives me a bias column. And if I take the columns out of here, I get out just the numeric data. And this right here is my matrix X. Okay, oops. So here is X. Okay. Likewise, I can create my vector Y for the points I want to predict. This is the MPG column of my original data frame. Here are my miles per gallon. I want to use X to predict Y. Okay. Now, it turns out that fitting this is not that hard once I know the analytic solution. So again, I can translate into Python the long matrix formula that I had on the previous slide. It's not too hard to do once I have it written down. It's X transpose times X inverse of this matrix multiplied by X transpose times Y. And it's a long formula, but this right here solves for me the parameters theta. This right here is theta hat. And it wasn't that hard to find. So what I've done here is fit a linear model to my data. I'll define this as fit linear. Okay. And now I have theta equal to fit linear. And here are my values theta. It's a little hard to interpret, so what I can do here is display it in a nicer way by putting it into a data frame. So I'll put here my column name, and I'll put here my weights. Okay. So what do I see here after fitting my model? I see that the intercept is, this right here is e to the 1, So this right here is negative 14 as my bias. This right here is times 10 to the negative 1 power. So this right here is negative 0.3. Okay. This is like negative 0.007. Right, this right here is negative 0.0003. Okay. So if I want to interpret this, I can try plotting them. Here's a bar plot of my theta, of my weights of my linear model. And it looked like this. Kind of hard to interpret. Why don't you talk with your neighbor about why this bar plot looks like this? Go ahead. Okay, I can guarantee you almost that you'll do something like this when you're fitting a linear model, and you'll plot the bar plot of model weights, and they'll look like this, and you'll have no idea why. Any ideas for why? Why it looks like this? Well, if you look at the numbers here, the numbers for the weights that actually correspond to input data are all very small, right? So we have here displacement to negative 3, like 10 to the negative 3, horsepower 10 to the negative 4. And if you look at my original data, you'll see here that these numbers in these columns are actually quite large. And if the numbers in the column are large, then the weights that correspond to the columns will be small. The reason why that happens is because the MPG doesn't vary that much when compared against these columns. So the MPG here is 32, but the weight here is 2,000. So any weight that I put in my model for the weight, oh, this is confusing. Let's talk about displacement. Any weight in my model that I have for the displacement column will be much smaller than MPG. It'll probably have to be something like maybe in the integer, like the below 10 range, or maybe like below 1 range. Okay? If I wanted to have these model weights, so in other words, okay, so I might be interested in looking at these weights because I might want to figure out which attributes contribute the most to MPG, right? So I might want to know whether, oh, does horsepower really determine MPG that well? Or maybe like I should look at the weight instead of horsepower. And the problem is you can't interpret these weights, or you can't directly compare them to each other because the magnitude of the weight depends a lot on how big the data are in your original data matrix. If you want to actually interpret these weights and compare them against each other, one thing you could do is standardize the columns of your data before fitting your model. By standardize, I mean I subtract the mean and divide by a standard deviation, which means I put all the values in here in standard units. If all the values in my columns are in standard units, then my weights will be more comparable. They'll all be around the same magnitude, which means I can compare them and try to figure out which ones are the most important. I won't go through that here, but you should keep that in mind if you're actually fitting a model to some data. Okay. Now I can do my predictions. Okay, so let's look at my predictions, which is, again, you just derived this, or you try to derive it, x at theta. And these are my predictions for all my data points. Let's call this pred, just for short. Pred, okay. And what I can do is take my original data. So these are my actual points, and I can put all these data into a data frame to compare them. Okay, so let's make a data frame. I'm going to say y is my y values. Y hat are my predicted values. The residuals are y minus my predicted values. I'm going to put a column here of n, which is just, I'm going to number each point from 1 to however many points I have. Okay. oops, comma, there we go. So these are my predictions, or my comparison matrix. Comparison. Okay. And oftentimes what I want to do for a linear model is plot the residuals. Just like for a simple linear model, I can plot the residuals. I can also plot the residuals for a multivariable linear model. I can also plot y against my predictions. I get this plot. So how do you think I should interpret this? So I have here y, which are my real values on the x-axis, against my predicted values on the y-axis. If I give you a plot with y hat on the y-axis and y on the x-axis, if my model is perfectly right for all the points, what do you expect to see? You expect to see a straight line with slope 1. Because if y hat is always equal to y, then when y is 10, y hat will be 10. When y is 20, y hat will be 20. When y is 30, y hat will also be 30. If it's not a straight line, then we can interpret it, we can look at how it deviates from that straight line and give that some meaning. In this case, I see that when y is 20, y hat is like usually bigger than 20. When y is, let's say 30, y hat is actually around 30. Right? So I could interpret this plot by saying my model here is more accurate for higher MPGs than lower MPGs. The reason why that might happen is because if I scroll all the way back up here to horsepower, let's go look at the horsepower. It turns out that it seems like the MPG has a nonlinear relationship with some of my variables in my data. And because it has a nonlinear relationship, the linear assumption of my model might not hold as well as I think it does. Okay. I can also see this by plotting the residuals. Let's plot the residuals. I have here n and resid. Okay, so I have my residual plot here, and it looks like what I should hope to see is that the points are scattered in like a random cloud around my 0 line. But it looks like they're not scattered around that cloud, like randomly. It looks like on this half of the graph, there are more positive values, more positive residuals, whereas between numbers 200 and 300, more negative values. And then on these values, on these cars here, we had them all over the place. Okay, so another sign that maybe a linear model is not the most appropriate one. But it turns out that linear models can be extended naturally to fit nonlinear relationships. I'm going to save that for tomorrow, since we're out of time for today. Instead, let's fill out attendance. And once you fill out attendance, we'll call it a day, and I'll see you tomorrow. Okay, open this up and do that. All right, and once you're done, that's all I have. So feel free to head out, and I'll see you tomorrow.